All right, picking up from where we left off, um, in general, any discrete probability distribution, which is what chapter 4 was on, discrete probability distribution, you're probably going to see me abbreviate prob and dist a lot because my handwriting on this template is only slightly worse than my handwriting on the board, which is not saying much. But any discrete probability distribution gets built with histograms. Remember, when we looked at the histograms, we said that any of this frequency data, the area inside painted by this histogram is the area equal 1. Each frequency bin had a probability. It followed the probability rules that whatever was within the bin had to be between 0 and 1 to be a probability, and all possible results added up to 100%. Well, for discrete or for continuous probability distributions, so for, whoops, did not mean to do that. Let me fix that here. Get this back to where it was. There we go. Sorry for that. That's what I get. There we go. Back here. All right, so any continuous probability distribution function, or any continuous probability distribution, we'll call a PDF, which is a probability density function. Because what we look for in a probability density function as it's graphed is we want to know how dense it is, how much stuff is between two x values. Remember how we said that continuous distributions always had a range of data. And so here I could be looking for x values that x is wedged between the max and the min. So there's some max and min, and that's going to paint in an area of the curve that's going to be equal to the probability. So we can talk about the probability between the max and the min as if it's how much paint has come across. And so this is what we do with probability densities. And the requirements on it is the function is trapped, the output of the probability function is trapped between 0 and 1, just like the discrete frequencies were. But the whole function value is trapped there. In fact, you'll rarely see it go near 1 because it has to fill all the space with 1. And the area under the curve equals 1. So, and when you say something's trapped between 0 and 1, this means it's never negative, which is, I think, how the book will say it. Never negative, and it's never more than 100%. If it was more than 100%, the area under the curve would go over 1. There are some exceptions to that in really, really advanced probability theory, and we have to figure out what that means in general. But for our sake right now, those exceptions and where they are and what they mean won't enter to what we study. So what ends up happening is we can get a variety of different graphs coming out, even though the values of some stuff are similar. So I look at a normal distribution here, and we have our inflection points, again, and our mean. These inflection points are symmetric. They're the same part about. And this shows me a mean of wherever the x value is here. In this case, I'm going to say 3.5. And a standard deviation of 1.5. So that means this inflection point is at 5, because it's 1.5 away from the mean, and this one is at 2, because it's 1.5 away from the mean. And remember, those inflection points are, right now it's facing down, where over here the curve faces up. And directions of curves have a meaning in if the value's rising or lowering. But for us, it's going to be a nice place to find on a graph. Well, I can have another distribution that's narrower, but the mean can still be at 3.5, right? But the standard deviation is only going to be 0.7. So these inflection points get sucked in, and most of my stuff is closer to the mean. Right? You see how that standard deviation pulls things in? And let's see, with a 0.7, that means it's 4.2 on this end and 2.8 on the other end. Right? And so we have a max and a min, and from our empirical rule back in chapter 2, which you should look at, there's 68% of the stuff is in there. Well, we can also move the mean. I can take this whole shape and have the mean moved. What we want to do is we want to create a curve that will work for anything for us. And so what we're going to do is we're going to create a standard normal curve. We're going to force some things on the standard normal curve. And so we're going to make a standard normal. So what is the standard normal curve? And so this is always going to have the same properties. And that property is the mean is going to equal 0. And the standard deviation is going to equal 1 for our curve. And so this will always center about the x-axis, and it will have an inflection point at 1 and -1. So at 1 and -1. And there's our mean equals 0. And so this curve will have the same answers for every value of x in it. And so what we really, really need to do is translate from whatever we have to the standard normal curve. And that translation, we already started. Right? So if we make the area of this equal 1, we can build a table of all the answers for each x value of how much stuff, what percent is up to that x value. Or in our case, we're going to say z value. And what we're going to do is we're going to use the z-score as our means of translating from what we have to this standard normal curve. So we can always talk. And so the z translation is we go, hey, whatever my data value is, minus the mean of my data, and that will now center everything around 0, because if I'm at the exact mean of my data, right, if my mean was, let's say if my mean was 58 and my x-score was 58, 58 minus 58 is 0. I've re-centered things around 0. And then if I divide by the standard deviation of whatever I have, well, now I'm counting in standard deviations, which is what we did in chapter 2. I said, hey, the z-score says if I get a z-score of 1.26, I'm counting by 1.26 standard deviations. Well, that means this map, the standard normal, translates to my z-score and back to what I'm working on. And so we can translate any x value into the standard normal. Now, there are some things in the standard normal that we have to take into account. All of these, and so if this is the standard normal curve, with this being at 0, mu equals 0, and it goes all the way to positive infinity and down to negative infinity. But that's really, mathematically we can't go from negative infinity to positive infinity. And so, we can't get there exactly. When you do the calculus on this and you calculate the area of the curve, it works. But for our cases and values in the book, what we'll say is if you look at a z of negative 3.49, Right? So if I come here and I count all the stuff up to a z-score of negative 3.49, it's really close to 0. The area up to there is close to 0. And so for what we're going to do with a 2 decimal place z-score, negative 3.49 is where we start counting. Anything before that is close enough to 0, it doesn't count. And on the other side, a z of 3.49 is close enough to 1. Right? There's so little stuff after it that we say that a z of 3.49 has 100% of the stuff in the area underneath the curve. Now this is an approximation we have to take because these things are meant to deal with infinity. And so the cumulative area increases. So from negative 3.49 up to 0, the cumulative area goes from 0 to now we have 50% of our stuff in there. And we work all our way up to 100%. And so what we want to be able to do is we want to find the cumulative area that corresponds with the z-score. All right, in the next video, we're going to use the tables in the book to look up cumulative areas, and we're going to use our calculator to work with cumulative areas. This is the standard normal curve. Law.